Hi everybody, I hope this video finds you well. In today's video, we're going to be working through practice number 6, which focuses on advanced probability. The problems here namely focus on conditional probability, the counting method, as well as binomial probabilities. To do these problems, you want to make sure that you've gone ahead and watched all the videos for advanced probability, as well as tried these questions sort of ahead of time. So if you haven't watched those videos yet, or if you haven't tried these questions yet on your own, I'd go ahead and pause this video and come back to it once you've had a chance to try some of these. If you have already tried these, well, let's go ahead and get started and take a look at these questions. So for question 1 here, we have this room that is full of faculty members from a university. We know that we have 30 faculty members overall, so we know that this totals up to 30 total. We can check that that makes sense because we're told that they're sort of divided or classified as follows. So we know that there's 5 math, 9 English, 4 science, and 12 social science. Putting those together, 5 and 9 is 14, plus 4 is 18, plus 12 does give us that 30. And we know we've also classified them not only according to what subject these faculty members teach, but also what type of faculty member they are. So for the math faculty, 2 of them are professors and 3 are instructors. For the social science, for example, 5 are professors and 7 are instructors. So what we're going to do in this question is we're going to look at some probabilities when we go ahead and randomly select 2 people from this room without replacement. And that without replacement basically means that once we've selected a person, when we go to select that second person, the first person can't be selected again. In other words, we remove that first person from the room. Now, if you notice in terms of the questions, parts A through F here are all just about the first selection. So for parts A through F, it doesn't really matter that we're selecting 2 people because all the probabilities we're going to be calculating in A through F are all about the first person. But in G and H, we will be calculating some probabilities about the second selection, so that's where it's going to matter that we're selecting 2 people and we're not replacing them after we make that first selection. So let's go ahead and determine each of these probabilities then. So for the first one here, we want the probability that the first selection is an English faculty member. Now, since this is the first selection, we're taking this person when there's still all 30 people in the room. So we know that this is going to be out of 30 because there's 30 people to choose from and they all have the same chance of being selected. How many of those people satisfy the outcome that we're looking for, or the event that we're looking for, which is that they're English faculty? Well, there are 9 English faculty members. So this probability should be 9 out of 30. The chance that when we go to pick that first person, that they are in English faculty is 9 out of 30, because there are 9 English faculty out of 30 total. All right, let's do the same thing for part B. First selection is a professor. Well, this time we don't care what subject they teach, just as long as they are a professor. So in terms of doing this, since this is the first selection, it's still going to be out of 30. All right, then when we go to select that first person, there's still all 30 people are in the room. In terms of the amount of professors, there's 2 and 3, which is 5, plus another 4, which is 9, plus 5, which is 14. So this probability would be 14 out of 30. For part C, we want the probability that the first selection is a professor and a math faculty. Remember, and means that they have to have both of these traits. So in terms of professors, we know that there's 2 professors here, 3 here, 4 here, and 5 here, but we also want them to be math faculty, so the only ones that are going to work are those 2 math faculty professors. This is still the first selection, so it's going to be out of 30, so 2 out of 30. And then finally, for part D here, the first selection is an instructor or a social science faculty. This is an or, so we can use that addition rule. So we can begin by looking for all the instructors. There's 3 there, 6, and 7. So that adds up to 16 out of 30. Then we can add to that the probability that they are social science faculty. We can see that there's 12 social science faculty right there. So we can do plus 12 out of 30. And then if you remember your addition rule, it said P of E or F is P of E, which we just did here, plus P of F, which we just did here, minus P of E and F, which was making sure that we didn't do any double counting. The and here would be anybody who was an instructor and social science, which would be those 7 people there. So we'd have to subtract 7 out of 30. We put that together, 16 plus 12 is 28, minus 7 is 21 out of 30. Now, could we arrive at this 21 out of 30 a different way? Sure. If we just go ahead and count and carefully avoid double counting anyone, we could begin by finding all the instructors, 3, 6, and 7, and then look for all the social science people that we haven't mentioned yet, which would be those 5 there. So 3, 6 is 9, 7 is 16, plus 5 is 21. So that would also get us 21 out of 30. Now, let's just do a quick separation here. Notice that these first 4 parts that we just did, they're all just standard probabilities, right? They were all just about that first selection. They weren't even conditional probabilities because we didn't have any extra information. Notice that for all of these, even though, we got different numerators, we always had the same denominator. It was always out of 30 because it was the first selection and we had no additional information. Parts E and F will be a little bit different because parts E and F are still about the first selection, but we have an additional piece of information, a condition, right? We know in this one that the first selection is an English faculty, for example. So parts E and F will be a little bit different. Let's see how to do those. For part E, we want the person to be a professor, but we have this additional information that they're an English faculty member. So remember, when reading these conditionals, the second thing you see is always the thing you get to assume has happened. It's the extra information. So we know that our first selection is an English faculty member. That means that instead of all 30 people being the possibility, we've narrowed it down to these 9 English faculty members. Now, out of those 9, how many of our professors? Well, we know it's 3. So this probability would be 3 out of 9. Notice we have a totally different denominator. Instead of being out of 30, it's out of 9 now because we have this additional information that the first person we're picking is going to be an English faculty member. All right, let's try the same thing with part F here. So this time, the additional information we have is that the first selection is going to be an instructor. So it could be these 3, these 6, or these 7. Notice that 3, 6, 7, that adds up to 16. So this is going to be out of 16. Once we know that it's an instructor, we've narrowed it down to 16 options. How many of them are science faculty? Well, none of them, right? There were no science instructors. So this would be 0 out of 16, which of course would simplify to 0. Meaning that this is an example of an impossible event. If we know that the first person we picked out is an instructor, then it's impossible that that person teaches science because there are no science instructors here. Okay, now let's turn to G and H. The big difference with G and H is that now the event that we're going to be looking at is going to be about the second selection. So we get information about who has already been removed, right? Who's already been selected the first time. And now we're trying to see what the probability is of the second one. So let's take a look at G. We know that the first person selected is a professor, and we want to get this probability that the second person is a professor. So let's think about the denominator first. Since we're on our second selection, it's going to be not out of 30 anymore, but out of 29, because we know that at least one, that we know exactly one person has been taken out of the group. So it's going to be out of 29. How many professors are there? Well, originally there were 2, 3, 4, 5. So that's 2, 5, 9, 14 professors. But we know that that first person who was taken out was a professor. So there's one less professor remaining. So that would make this probability 13 out of 29. There are only 13 professors remaining from the original 14, and there are only 29 people to choose from the original 30. All right, let's try the same thing here. Second selection is a science faculty, given that the first selection is a math faculty. So again, since this is the second selection, it's going to be out of 29. What's the chance that the second selection is a science faculty? Well, there were 4 science faculty members originally. We know that the first person taken out was a math faculty, so this has been 5 down to 4, but all 4 science faculty members still remain. So this would be 4 out of 29. So there we go. These two probabilities, the big thing that's sort of shared here is you'll notice that they're both out of 29 because both events were about the second selection based on information from the first one. All right, so this first question was all about calculating sort of some basic probabilities here, as well as some more advanced probabilities, specifically conditional probabilities. And again, conditional probabilities, you always take that second thing, the thing after the vertical line, as your additional piece of information, and that is going to have a direct impact on the denominator of your probability. All right, let's go ahead and now take a look at question 2, which started to get into sort of calculating some of the advanced probabilities using our two methods, the counting method and the binomial. So for question 2, we're selecting marbles from a bag, and the bag consists of 15 blue marbles, 11 reds, 20 yellows, and 4 greens. We probably want to make a note real quick of how many total that is. 15 and 11, that sounds like 26. Plus 20 is 46, plus 4 is 50. So we have 50 total here. We're going to select 7 marbles randomly without replacement. Of course, that should make sense. Once you take a marble out, you're not going to put it back in. So you're taking 7 out, so none of them can be chosen twice. Now, and what we want to do is we want to calculate each of the following probabilities. And we want to try to make sure to write our answer as a decimal. All right, so a couple things to notice here. First is we're taking out 7 marbles. So we have multiple selections. The reason that that's important is because most of the basic probability that we did was only like when we took one thing out. If we were only going to take one marble out here, we wouldn't need to use any fancy probability techniques. We would just simply count up how many satisfy the event and divide by the 50 that are in there. But we're taking out 7 marbles. So this is a more complicated situation. We have to use one of our methods. The other thing to sort of make note of here is that since we have this without replacement, that tells us that we're going to be in a dependent probability situation. What do we mean by dependent? Well, we mean that the probabilities are going to change as we go along and do this. Because if you think about it, if you pull out at the beginning a couple red marbles, there's going to be less red marbles later on. So the probability and what remains in the bag is going to change. That makes it a dependent probability situation. Remember that when we have multiple selections and a dependent probability selection, these two things imply that we want to use that counting method, which is where we're going to use those combinations, that NCK, to actually help us do this. All right, so let's see if we can do that. The first one we want to do is the probability that we get all blue. Well, let's first start by thinking about our denominator. For our denominator, we've got 50 total marbles, and we're going to choose out 7. Remember, they can't be replaced, so the same one can't show up twice. And of course, the order in which we pick them out doesn't matter because we're just taking out 7 at a time. So we can count that as 50C7. Remember, this combination counts out the number of ways we can choose these without replacement and where the order doesn't matter, which is exactly what we want here. The numerator then is going to correspond to our event, all blue. If we want to pick all blue ones, we have to choose only from the 15 blue. How many do we need to choose? Well, still 7 because we're selecting 7. So it's going to be 15C7. So this will do it here, except we did want to get a decimal, so we'll have to use our calculator. Remember to do that, to go ahead and do the numerator, we type in 15, then hit Math, PRB, go to NCR and put the 7, and hit Enter. And that'll give you your numerator, which in this case should be 6,435. And then in the denominator, we do the same thing. Type in 50, hit Math, go to PRB, go to NCR, and then hit 7, and then hit Enter, and we get this crazy huge number, 99884400, which should make sense. There should be tons and tons of ways of picking 7 marbles out of 50. Then we can go ahead and do this division. 6435 divided by 99884400. We get a very, very small number. This is approximately 6.4 times 10 to the negative 5th. On your calculator, it comes out as e to the negative 5th, which means 10 to the negative 5th. This 10 to the negative 5th means to move. You can just leave your answer like this, of course, that's fine. But if you want to write it out completely, this 10 to the negative 5th means that you move this decimal place 5 times to the left. So once, twice, 3 times, 4 times, 5 times. Notice that that's going to put 1, 2, 3, 4 zeros in front of this. So this would be 0.00064. So an incredibly small number. Does that make sense? Well, of course, right? There's 50 marbles in there. Only 15 of them are blue. So getting 7 blue ones in a row, considering that as you take blue ones out, there's less blue ones later, it should be very hard for that to happen. So the probability is very low. Keep in mind this answer or this answer are both appropriate. If you want to leave it in what is called scientific notation, that's totally fine. All right, let's take a look at B, which we should be able to do the same way. One big tip for working on probability questions is once you find a method, you want to stick to using that, right? The choice of using this counting method, these combinations, are because there are multiple selections and it's dependent. That's going to be true throughout the entire problem. So every part of this should be able to be done with this method. So let's do the probability that we don't get any yellow, so no yellow. All right, so let's think about our denominator. We're still choosing 7 marbles from the 50 total. Keep in mind that denominator isn't going to change unless for some reason the problem tells us that we change the contents of the bag or we change how many marbles or things we're selecting from it. So for pretty much all of this problem, considering we don't have any information like that, the denominator is going to be 50C7 each time. Let's figure out how we can make sure that we select no yellows. Well, by selecting no yellows, we want to avoid the yellows, selecting either blues, reds, or greens. So, since there's 15 blues, 11 reds, that's 26, plus 4 greens, that's 30. So we have 30 marbles to choose from to avoid the yellows, so it'll be 30C7. Now, we can go ahead and type that into your calculator. If you want to type it all in at once instead of doing bit by bit, just make use of some parentheses. Put a parenthesis, then put 30, math, go to PRB, hit the NCR, put 7, close up a parentheses, divide, put another parenthesis, put the 50 in, then hit math, PRB, go to the NCR, put the 7, close up the parenthesis, and hit enter. And after all that, you should get as a decimal 0.0204. So right there, you'll notice that we got basically about a 2% chance. So basically what we're saying there is if we reach into this bag and pick out 7 marbles, the chance that we do not have any yellows, so meaning we get some mixtures of blue, reds, and greens, is about 2%. All right, let's see about part C here. We want the probability that we get 2 blue, 1 red, and 4 yellow. So again, we're still choosing 7 from 50. So the denominator is going to be 50C7. For the numerator, we'll just count each of these. First, we want to choose 2 blue. So we have 15 to choose from. So we can do that as 15C2. For the 1 red, we have 11C1. So 11C1. And then finally, for the 4 yellow, we've got 20 to choose from. So we have 20C4. Remember, as we discussed in the counting sort of section about how you sort of count when you have multiple options, remember the operation we always use is multiplication to glue these all together. So if you're going to type this into your calculator, make sure you put parentheses around each of these to make sure it gets typed in correctly. If we go ahead and do that, so put in parentheses, 15 math, PRB, hit that NCR and then 2. Close up the parentheses, then hit times again, new set of parentheses, 11, math, PRB, put in that NCR, put the 1, close up the parentheses again, times, one more set of parentheses, 20, math, PRB, NCR, then pick 4, then put a division, last set of parentheses, 50, math, PRB, get the NCR, and 7, and then hit enter, and after all of that, we should get the decimal 0.0560. So there's about a 5.6% chance that when we pull out our 7 marbles, we get this exact combination of 2 blues, 1 red, and 4 yellows. All right, let's look at part D, the probability that you get exactly 3 yellow. The thing we have to be careful with here is that while we want exactly 3 yellow, we have to remember we're still selecting 7 marbles. So probably helps to say that we want 3 yellow and 4 non-yellow. The reason we have to have 4 non-yellow is we want exactly 3 yellow. So we can't have 3 yellows and then another yellow. We have to have 3 yellows and then 4 non-yellows. And of course, these 4 non-yellows means blues, reds, or greens. So again, denominator still going to be 50C7. The 3 yellows can be selected from the 20. so 20C3. The 4 non-yellows can be selected from the 15, 11, and 4, so that's 30. So 30C4. So if we go ahead and do that, so we can put that into our calculator, and once you do that, what you should find, as we just do that real quick, you should find that that comes out as 0.3128. So there's about a 31% chance that you end up getting exactly 3 yellows. So that means 3 yellows and 4 other things that are guaranteed not to be yellow, but could be any mixture of blue, red, or green. All right, let's do the probability you get exactly 2 green. So same idea. So this would be 2 green and 5 non-green. So first, let's count up the ways we can choose those 2 greens. There's 4 greens to choose from. So that would be 4C2 times. Then we need to choose 5 things that are not green, so we avoid those. 15 and 11 is 26, plus another 20 is 46. So we've got 46 to choose from, and we have to choose 5. And then divided by 50C7. Then we can put that into our calculator. 4C2 times that 46C5, and then divide that whole thing by the 50C7, and we should get that that comes out as about 0.0823. So there's about an 8% chance that when you get your 7 marbles out, you have exactly 2 green, along with a mixture of 5 non-green ones that could be blue, yellow, or red. All right, last one, the probability that all the marbles you get are green, so all green. Well, if we think about that, we've got 4 green ones to choose from, and we need to choose 7. So I guess we would say that that's 4C7 over 50C7. But hopefully, even before we go to type that into our calculator, we should already know what this is going to come out as. If there's only 4 green marbles, and we want them to all be green, but we're choosing 7 of them, that's impossible. So if you type this into your calculator, or just use common sense, this will come out as 0, because this is an impossible event. All right, so in this question 2, we used what we call the counting method, which is basically making use of this combination counting technique for both the numerator and the denominator. Remember that in each of these, the numerator corresponds to the event that we're actually looking at, whereas the denominator stayed the same in each one. That was just based on how many total things were in the bag or the group that we're selecting from, and how many we need to pick out. All right, let's move to question 3, which talks about what to do when you have multiple selections, but things are independent, meaning the probabilities don't change as you do more and more of the selections. So for question 3, we're going to suppose that you're studying the choice of major at a large university. So suppose you know that there's a 6% chance of a student being a math major at this university, and that each student's choice of major is independent. And this is really the key word here when we see that independent. We're also going to suppose that you're studying a random group of 13 students from the school. Why is it so important to pick up on this word independent? Well, as soon as you see that word independent, you start thinking about the binomial probabilities. So let's check this real quick to make sure that this really satisfies what it means for something to be a binomial probability experiment. So let's do that off to the side. So that word independent is what sort of encourages us to do this. First, we need to know, are there 2 outcomes? Well, we're basically interested in whether or not these people are math majors. So the answer is either yes, they are, or no. So there are 2 outcomes, math major or not. All right, so obviously there's tons and tons of different majors, but since we're only interested in whether or not they are a math major, we've made it where there are only 2 outcomes. Is everything independent? Well, that's told to us, so we know that that's true. So it is independent. And then lastly, do we know the number of trials and the probability of success? Well, the number of trials should be easy. It's 13. We have a group of 13 students. And the probability of success is 6%. As a decimal, we'd say p equals 0.06. So we do have those. Now, keep in mind, for the binomial formula, it is very useful to have the probability of success along with the probability of failure. So we'll make a little note. 1 minus p is 0.94. And that should make sense. If there's a 6% chance that somebody is a math major, there's a 94% chance that they are not a math major. All right, so let's go ahead and do each of these. We can take a look at this first one. Now that we know it's a binomial, that's what we're going to use. So the probability that we get exactly 3 math majors. Well, remember that binomial formula that we covered in the videos is exactly what we want to use when we have an exact amount of successes. So we'll take the number of trials, 13C3. We want 3 successes. Take the probability of success, which is 0.06. Raise it to the number of successes. Take the probability of failure, 0.94, and raise it to the number of failures. Well, how many failures do we want here? Well, if we want 3 of them to be math majors and we have 13 students, that means we want 10 to not be math majors. So we have 13C3, 0.06 to the third, 0.94 to the 10th. We can type that in just as it looks, so 13, then math, PRB, C3, then times, parentheses, 0.06 to the third, and then times, parentheses, 0.94 to the 10th. And when we do all that, we should get approximately 0.0333. So there's about a 3% chance that exactly 3 of these 13 students are math majors at this school. Okay, let's see about B. What is the chance that exactly 5 of them are math majors? Same idea, exactly 5 math majors. Well, we have 13 students to choose from. We need to choose 5 to be the math majors, 0.06 to the 5th. And then how many do we not want to be math majors? Well, if we've got 13 students and 5 are supposed to be math majors, then 8 are supposed to not be math majors. Remember, these exponents always need to add up to the number of trials. Then we can go ahead and type that into our calculator. So 13C5 times that 0.06 to the 5th times that 0.94 to the 8th. And again, we should get a very sort of small value here. So we get approximately 6.1 times 10 to the negative 4th. You can leave it like that, or you can move this to the left 1, 2, 3, 4 times. And we should get that is 0.00061. So a very small likelihood that exactly 5 of the 13 students are math majors. All right, now we have some slightly harder ones in C and D because it's not going to be an exact amount we want. So now we want the probability that we get less than 3 math majors. So what would satisfy less than 3? That would be the probability that we get exactly 0, 1, or 2. Right? The way we would get less than 3 of them would be if none of them are math majors, 1 is a math major, or 2 are math majors. All of those would satisfy less than 3. So what are we going to do this then? Well, we'll make use of this formula that we've been using 3 times, 1 for each of these possibilities. So the first one for exactly 0 would be 13C0, 0.06 to the 0, 0.94 to the 13. That's everybody not being a math major. Plus, because again, we don't care if it's this or this or this, all of those are less than 3. So we'll add this. 13C1, 0.06 to the 1, 0.94 to the 12th. That's 1 being a math major and 12 of them not being math majors. Plus 13C2, 0.06 squared, 0.94 to the 11. That's 2 of them being math majors and 11 not being math majors. So let's go ahead. We'll write out what each of those come out as. This one, if you want to be fancy, does simplify just to 0.94 to the 13 because 13C0 is 1 and 0.06 to the 0 is 1 because anything to the 0th exponent is 1. So the first one, if you want to be fancy, you can just type in as 0.94 to the 13. So the first one should be 0.4474 plus the next one should come out as 0.3712 plus the last one, 13C2 times 0.06 squared times 0.94 to the 11. should get that as 0.1422. Sum all those together, so 4474 plus 0.3712 plus 0.1422. Looks like that should come out as 0.9608. We'll just sort of close that off so we don't blend that into the next one. So the chance that we get less than 3 of these 13 students to be math majors is basically about 96%. All right, last one. We want to do what is the chance that more than one of these students are math majors? So probability more than one math major. So what would satisfy more than one? Well, that would be exactly 2, 3, 4, 5, 6, all the way down to all 13 of them being math majors. Now, we could try to do this the same way as we did this one, but notice that we'd have to use our formula 1, 2, 3, 4, 5, 6, 7, a bunch of times. We don't want to have to do that, all of that. So what we can do here is we can make use of that other probability rule we introduced at the end of our basic probability discussion, the complement rule. We can look at this at 1 minus the probability of whatever outcomes are not on this list. Well, what are not on this list? Well, this is 2, 3, 4, 5, 6 down to 13. So things not on this list are 0 and 1. The probability that none of them are math majors, or the probability that just one of them are math majors. So this would be the probability of exactly 0 and 1. And notice we just calculated those. Exactly 0 was right here, and exactly 1 was right here. So we can do this as 1 minus 0.4474 plus 0.3712. And if we go ahead and put all that together, make sure you do the stuff in the parentheses first, so 0.4474 plus 0.3712, and then 1 minus that, you should get 0.1814. So there we go. There's our probabilities there. Now we're going to finish this up by considering a slightly different size group of students. So in parts A through D, we were doing 13 students from this school. Now we're going to imagine that we have 800 students from the school, so a much larger group. And of course, when we have a really large group like this, we don't like to try to use this formula that's good for small groups and exact amounts. So for parts E and F, we're going to use what is called the normal approximation to the binomial. But to do that, we have to confirm that it's actually appropriate. I mean, we sort of all feel that 800 is large enough, but when we discussed this, we did give a way to confirm that something like 800 in this situation is large enough. So let's confirm that it's appropriate to approximate this situation with a normal random variable. So how do we do that? Well, we discussed that what you need to confirm is you need to check that np1 minus p is greater than or equal to 10. So let's check that. Since we're now talking about a group of 800, the n will be 800. The probability of success, well, that's still the same. We're still talking about the same school, so 0.06. And of course, the 1 minus p, that's the probability of failure. That will be 0.94. So let's go ahead and multiply all those together. 800 times 0.06 times 0.94. What we should get here is we should get 45.12. What sort of matters about this? Well, we want to make sure that this is greater than or equal to 10, and it certainly is, so we can put our little check mark there, and that means that the normal approximation is appropriate. Okay, perfect. So now let's go ahead and use this normal approximation for part F, which is to say what is the chance that less than 35 of these students are math majors. So let's go ahead and see how we would do that. Now that we know this normal approximation is appropriate, we can go ahead and get the mean and standard deviation. So remember that for a normal distribution, it's entirely defined by its mean and standard deviation. So when doing a binomial like this, the mean will be n times p, which in this case is 800 times the p, which is 0.06, the probability of success. If we go ahead and do that, 800 times 0.06, we should get that is 48. What does this value mean? Well, what we are basically saying is if we have 800 students and 6% of them are supposed to be math majors. Well, 6% of 800 is 48. So on average, out of every 800 students, we expect 48 of them to be math majors. For the standard deviation, we're going to do the square root np1 minus p. That's our formula for standard deviation for a binomial. In this case, that's going to be the square root of 800 times 0.06 times that 0.94, which is the probability of failure. Now, if you want to be a little fancy, this in here, you don't need to retype in your calculator. This is exactly what we had here. So we just need to do the square root of 45.12. And we should get that is approximately 6.72. And in terms of units, if you want, this would both be in students who are math majors. So we're saying that on average, we expect 48 out of the 800 to be math majors with a standard deviation of 6.72 math majors. All right, now let's go ahead and use our normal distribution. So since it's normally distributed, we can draw our bell-shaped curve. We can go ahead and put the middle at 48. Our point of interest is 35, which is going to be somewhere over here. And we want less than 35, so we will be shading in the stuff to the left here, which is good because that's what table A shows us. Now we need to find the location of this relative to the mean based on the standard deviation. Remember, that's just the z-score. So our z here will be 35 minus 48 over 6.72. So if we go ahead and we do that, 35 minus 48, and then divided by 6.72. Now we should get that as negative 1.93. Okay, now that we have that, we want to go ahead and look that up on table A. So we'll have to go find table A real quick. Let's go ahead and do that. This should be way down in here. Apologize for this. Let's go ahead. Normally I would have it set up there, but we want our statistical table. So there we go. We want table A. Oh, that's not the right spot. We just want to reference a table A here. We can just grab one from one of the previous things. Okay. All right, here's where we start discussing the normal distribution. There we go. So what are we looking for here? We want a negative 1.93. So there we go. There's negative 1.9 and the 0.03. So there's our probability, 0.0268. So let's go ahead and take that 0.0268. And again, so we should get that 0.0268. Keep in mind, table A always tells us what's to the left. So that does line up with what we want here. So 0.0268. So what this tells us is that the probability that less than 35 are math majors should be equal to 0.0268, or approximately equal, since this is just an approximation. There we go. All right, so the key thing to think about here is that for our class, you're not expected to sort of guess when to use this normal approximation. A question will always sort of lead into it by confirming that it's appropriate to use it. You're never going to have to use it when it's not appropriate. So you'll always get this sort of hint to confirm that it's appropriate to approximate. Once you confirm that it's appropriate by checking the np1 minus p greater than or equal to 10, then you can go down your normal, pardon the pun, normal distribution approach, find the mean and the standard deviation according to these two key formulas, use your bell-shaped diagram, calculate the z-score, and use table A as standard. That wraps up practice 6.